Hello everyone, today we'll talk about the problem count subarrays where max element appears at least k times. We're given an integer array nums, positive integer k, and we have to return the number of subarrays of the array nums, where the maximum element of that array nums, so not the subarray but the whole array, appears at least k times. A subarray is of course a contiguous sequence of elements. If you want to try to solve this problem yourself, then feel free to do so. And now I'll just say that we're on a streak of very similar problems, which you'll probably notice if you have already looked at 2 previous dailies. And if not, you can try to solve them, or perhaps look at my videos that explain how to solve them. And the fact is that while this problem seems a little bit different, there is some funky stuff with the maximum element. There is something that it has to appear at least k times and not at most k times. I think the simplest solution, especially for somebody who has already solved yesterday's problem, is to make one simple observation, and then you can actually reduce this problem to a simpler version of yesterday's problem, actually a simpler version that I discussed back then. To begin with, let's say that we, before doing anything else, traverse the array once and figure out the maximum element in that array, which we'll call v. It's of course simple to do by yourself. You also have functions in C++. You have max element, which you then have to dereference because it returns an iterator, and in Python you just have the max function. Now the crucial idea here is somewhat similar to an idea that is often used in probability theory when you're calculating a probability of something. Well, you know that the probability of something happening and of that thing not happening always add up to 1. And so in this case we know that let's say the percentage of correct subarrays of our array plus the percentage of incorrect also add up to 100%. Or in other words, the number of correct subarrays plus the number of incorrect subarrays equals the number of all possible subarrays. If you don't know the formula for the number of possible subarrays for an array of length n, then I encourage you to come up with it and try to prove it. And now a reminder for all the others. That formula is of course the length of the of our original array times that length plus 1 divided by 2. At the end of this video I will show you, let's say, 2 example ways of actually coming up with this formula. But right now we just have to know that this formula exists. And of course if you are solving this problem yourself, you'll notice that the signature of the function has it returning a long. That's because of course this is a quadratic with respect to the length of the original array, right? So this is O of n squared, if n is the length of the subarray. That's not like the time complexity, although if you were to enumerate all the subarrays that would be the time complexity. But this is also the complexity just of this term, which is also something that we can talk about. And now essentially we have reduced our problem to what we know already, because we have to take this and then we have to subtract all the bad arrays. And of course bad arrays in this case are arrays where our value v appears less than k times, or at most k minus 1 times. And this is exactly the problem that we know how to solve, because this is a simpler version of yesterday's problem. And now let's look at the code. So we can see that, as I said, the signature returns long. Now if you're, let's say, coding on a whiteboard or pen and paper, and this is not something that was specified, then it's either good to ask about it, if the answer will always fit within an int, or perhaps to notice that the answer might not fit within an int and then declare it as long instead. Or perhaps just use Python and not worry about any limits. So the first step is to determine our interesting value v, which is max element in nums. And of course, since this is an iterator, we have to dereference it. And this should be familiar to all of you. Left end, right end, we push the right end forward. If the number here is not interesting, then we just add all the possible subarrays we can make that end on j. If it is our value v, we increment the count, and if the count is now too big, right, because we want to count those that are less than k, then we just push I forward, and we hope to find v while pushing I forward. And in this case we can decrement the count. And of course, so this is the number of, in this problem, incorrect subarrays, and this is the number of correct subarrays. And also, sometimes it's necessary, sometimes not. I like to typically either use longs for everything, though this is quite inelegant, or just, when you're multiplying stuff, you can just start with a 1 that is 1 of type long, so you can write 1ll, and then everything to the right, it'll be automatically promoted to a long. And let's quickly talk about this formula. One, let's say, intuitive way of coming up with it is to notice that every subarray has to start at a certain element. If it starts at the first element, we have n different options for its length, because it can just have 1 element, 2 elements, perhaps all the n elements. If it starts at the second element, then we have n minus 1 options. So all the previous options, but we cannot take all elements because we cannot take the left one. So then there we have n minus 2 for the second element, so on, 3, 2, 1. And of course, since those are all different subarrays, and those are all possible subarrays, because every subarray has to start somewhere, then this is the answer. And to show that this is equal to this, I think the simplest way is to notice that we have n elements, and by using the classic method of noticing that the first element and the last element have a sum of n plus 1, and now the second element and the penultimate element also have sum of n plus 1. So all these elements, when we pair them up, and perhaps if n is odd, then the middle element will be left out, have value of first element plus last element divided by 2. And this is exactly our formula. And another way of thinking about it is that if we are given the original array, then we can represent our subarray as something like placing the opening bracket in some place, closing bracket in another place. And possible places also include before the first element and after the last element. And so there is one more option than the number of elements, and we can count the number of correct ways of placing these brackets. And so any way of placing these brackets will be a pair of I and j, all of them going from, let's say, 1 to n plus 1. But now there are two problems. One problem is that I and j can be equal. So if I and j are equal, then we would have something like this. This is not allowed in our solution. How many ways are there of doing that? Well, there's only n plus 1 positions where this can happen. And of course the original number of ways is n plus 1 squared. So we have n plus 1 squared, pairs of ij, n plus 1 bad pairs, where our subarray is empty. And another problem, even when I and j are not equal, is that perhaps j is to the left of I. So we would have something like this is the left one, and this is the right one. So it's also incorrect. But luckily we can notice that now that I and j are different, then for every correct one, if we swap them around, we get an incorrect one, and if we swap them around again, we get the same correct one. So we have a bijection between correct and incorrect ones, and so the count of correct ones is this divided by 2. And of course this all simplifies, so we have n plus 1 times n plus 1, and we take away 1 n plus 1, so of course this happens to be n times n plus 1, still divided by 2, so this is what we wanted to get.